So, hi everyone and welcome to the video 5 of S block elements. In today's section, we will be taking a look into the alkaline earth metal with respect to the uses of alkaline earth metal, different compounds of alkaline earth metals, properties, and we will end up the entire session by anomalous properties of beryllium. Okay, so let's start with the first one, and that is going to be with respect to the uses. So, the uses of alkaline earth metals. Okay, so in alkaline earth metals, we'll start up with the first one, and that is going to be beryllium. Right? So, when we take a look into beryllium, the first and foremost use of beryllium is that it is used in the preparation of different useful alloys. One of such alloys is with its combination with copper, that is the copper beryllium alloy. Okay, now this copper beryllium alloy is used in the preparation of alloys which are used as an high tensile spring. Okay, so therefore this particular alloy which is prepared is used in preparations of high strength springs. Okay, so in the springs we use this particular alloys. Now, when we take a look into the next one, and that is going to be magnesium. Again, magnesium is used in the preparation of alloys. Its combination, that is its alloy with aluminium, that is magnesium aluminium alloy. This alloy is very light. Of course, it's strong but very light, and therefore, as it is tough, that is strong, and light in its nature, okay, due to this particular property, they use this alloy in the preparation of aircraft components. So, it is a combination of magnesium with aluminium. Okay. While if we see the different uses of magnesium, magnesium carbonate is used as a part in the toothpaste. Okay, so this is the use of magnesium. If we look into the use of calcium, calcium is used in extraction of different type of metals from its oxide. But usually we use carbon in such cases, but in cases where carbon is not used or extracting a metal from an oxide using carbon becomes tougher process, we use calcium over there. Okay, so now this particular calcium is used in extraction of metals from their metal oxides. In the situation where we cannot extract metal from metal oxides using carbon, in such particular cases we use calcium. Okay, now taking a look with respect to radium. Now, radium is used in radiotherapy. It is used in radiotherapy in the treatment of They use it in the treatment of cancer. Okay, so these were the different uses of alkaline earth metals. Moving forward with the next one, and that is going to be the general characteristics of compounds of alkaline earth metals. Okay, so now when we start with this, we start with the first case, and that is going to be the oxides and hydroxides. Okay, now when we are taking a look with respect to oxides and hydroxides, okay, now we need to understand that which are the metals which can give these oxides or hydroxides, what is going to be the trend in it. Okay, so whenever we take an alkaline earth metal and as we heat this under the presence of air, okay, so as we burn this under the presence of air, except for beryllium, all other elements of the alkaline earth metals will get oxidized in order to form metal oxides. Now please observe the representation here. It's simple as MO. Okay, because here all the metals of alkaline earth metals exist in a form of M+2 state. Okay, and so therefore oxygen what we have is -2. Upon combination it will just give us as MO. Okay, so now what was happening here? Except for beryllium, all of them burn in air in order to form oxides. That is a metal oxide. However, when we compare this metal oxide with beryllium oxide, okay, we can obtain the beryllium oxide by other processes, and when we have this beryllium oxide and other elements of alkaline earth metals in combination with oxygen in order to form oxides, when we compare these two, okay, what we see is beryllium oxide is amphoteric in nature. Now, what is amphoteric? That is, it can react with acid as well as it can react with the bases. Okay. Beryllium oxide is covalent in nature. Okay. Now, when we compare this thing with the other elements in a sense, we have magnesium, we have calcium, we have strontium, we have barium, right? These particular oxides, when we observe, what we see is these particular things are actually basic in nature. Okay, they are basic. This is amphoteric. Secondly, when we take a look over here, all of these are ionic in nature. So this is the major difference between beryllium oxide and other metal oxides of alkaline earth metal series. Now, on the other hand, when we take this and as we take it and react this one with water. Okay, as we react this with water, all of these have a tendency in order to get converted into their respective metal hydroxides. They are getting converted into metal hydroxides here. Okay. So now, when we take a look into these metal hydroxides which are formed, Okay, these metal hydroxides solubility thermal stability and their basic nature of metal hydroxides. These characters will go on increasing as we go down a particular group. Okay, that means as we travel right from magnesium to barium. Okay, what will happen? Solubility will increase, thermal stability will increase, and basic nature will increase. Okay, so these are the points with respect to the metal hydroxides. Now we will take a look into one simple reaction. Now, as we are speaking about the metal hydroxides, we will check one particular reaction with respect to the beryllium hydroxide. So, beryllium hydroxide is amphoteric in nature, just as the way as beryllium oxide was amphoteric. Beryllium hydroxide is also an amphoteric in its nature. Okay, so therefore what is going to happen is, as it is amphoteric in nature, this particular beryllium hydroxide can react with both acid as well as with the base. First, we'll observe its reaction with a base. Okay, so with a base, when beryllium hydroxide reacts, so BeOH twice plus 2 times OH minus. Now, OH minus is nothing more than an hydroxyl group which is donated by a base. A base is a substance which can donate us OH minus. So, I am not taking the other counterpart of this. We will react these things, and what we observe is, we get over here BeOH 4 times minus 2. Okay, so this is called as berylate ion. Okay, so this is our berylate ion over here. On the other side, as we said that it can also react with an acid. So, with acid, when it starts reacting, we'll take one example over here, that is BeOH twice plus 2 times HCl plus under the presence of water. Okay, what will happen is, it will give us almost same composition but with a smaller change for berylate ion. Okay, now this particular compound, we call it as tetra 4 aqua OH beryllium Be, oxidation state of +2, chloride. Chloride should have been written over here, please. Observe, we need to write the chloride over here in continuation. Okay. So, what we have is tetra aqua beryllium 2 chloride is the name of this particular complex. So, as we have beryllium hydroxide reacting with both acid as well as with the bases, we call these particular character as an amphoteric. Alright, so let's observe the next character, and that is going to be the halide. Now, let's speak about the next type of compounds, and that is going to be the halides. Okay. Now, halides are nothing more than the combination of the substances with halogen. Okay. And in this particular case, can we say that halogen, whenever it combines in the form of X minus, and as it is a metal which is going to be under consideration or combination, we'll take it as M plus. Right? But these metals of alkaline earth metal series, they are in the form of +2. As it is in the form of +2, we require 2 halogens in combination Therefore, we represent it as MX2. So, in this particular case, MX2s are nothing more than your alkaline earth metal halides. Okay, so as we see over here, the first case is that when beryllium combines with halogens in order to give us beryllium halide is again an exception when we compare it to the other elements of the series. Other elements of the series, that is MX2, wherein M will represent to us, which are magnesium, we have calcium, strontium, and of course we have beryllium. Okay, now in this particular case, what happens is when we observe these particular elements, these elements will give us ionic compounds. That means these compounds are having ionic in nature. Okay, while BeX2 forms covalent in nature. So BeX2 is covalent in nature, while the other elements form the halides which are ionic in their nature. Okay, so now when we observe one of the examples such as BeCl2, now this particular compound exists in the form of chain type of structure. It is in the form of dimer chain because of stability. If it wants to be stable, it forms a chain kind of structure. And the chain kind of structure is represented as BeCl, Be, over here, Cl, again Be, and this thing continues. Okay, here Cl, Be, Cl, this angle is 98 degrees, while the bond length from beryllium to chlorine is 202 picometers. While the distance between the two berylliums is 263 picometers. Alright? One more thing about this beryllium halides is that these particular things are soluble in organic compounds or organic solvent. Organic solvent such as you can say as benzene, carbon tetrachloride, carbon disulfide. Okay, so such kind of solvents wherein BeX2 is soluble. Now, going forward with the next one. So, the next section is the oxo acids or the salts of oxoacids. So, under the section of salts of oxoacids, we have three categories, out of which the first one we have is the carbonates. Okay, let's complete first with carbonates and then we'll enter into the sulfates and the nitrates. Okay, so when we have this carbonates, first thing is how do we prepare these carbonates? We prepare these carbonates by having a solution of alkaline earth metal salts, such as the chlorides or sulfides or whatever it is. Okay, so when we have this, and we react solution, we are going to react the solution with sodium or ammonium carbonate. So we are going to take sodium or ammonium carbonate, insert it into this alkaline solution, metal salt solution. Okay, and as it starts to react, it will produce sparingly soluble particles. And these particular particles, which are sparingly soluble, are nothing more than, what we have is, these are nothing more than the metal carbonates. Now, these particular metal carbonates which are obtained, these on heating, okay, they decompose, they break down. So therefore, let's observe M will represent a metal of alkaline earth metal series, and we have a combination with MCO3. Now remember, CO3 has a charge of -2, while as the metal of alkaline earth series has a charge of +2. Quite simple as that. Okay, so when we combine them, what we get is MCO3. Now, when we have this MCO3 and as we start to heat it, so it will give us metal oxide. Along with metal oxide is going to give us carbon dioxide, which is going to be eliminated. Okay, now again there is an exception with respect to metal carbonates of these and beryllium carbonate. Now beryllium carbonate is highly unstable. Okay, of course it will decompose in the same manner, giving rise to beryllium oxide along with the byproduct as carbon dioxide. Of course it is going to go in the same manner, but this is highly unstable compound. When you just keep it open in atmosphere, it will get decomposed. Okay, so therefore in order to avoid the decomposition, what they do is they take this particular beryllium carbonate and they keep it in the atmosphere of carbon dioxide. So it is preserved in atmosphere of carbon dioxide. So this is how we have to observe the different trend, the different properties. Okay, this is an exceptional case which we have to remember. Alright, so let's move to the next one, and that is going to be the sulfates under oxo acids. Okay, so under oxo acids we have already seen about the carbonates. Now it's time for the sulfates. Now when we pick up the sulfates, these particular sulfates are actually white in color. Okay, they are white in color, and among the sulfates it is the beryllium sulfate, while magnesium sulfate, which are readily soluble when we put it in water. Okay, so therefore these two things are readily soluble in water. Now question is, why are these two only readily soluble in water rather the other elements, that is right from the calcium, strontium and barium? Their solubility goes on decreasing with increasing size. Here these particular compounds are soluble because of the small size of beryllium plus 2 ions and magnesium plus 2 ions because of these two things. Okay, because of the smaller sizes of beryllium and magnesium and higher hydration enthalpy. Because of these two reasons, magnesium sulfate and beryllium sulfate are easily soluble in water, while the solubility decreases from calcium to barium. Okay, here the solubility goes on decreasing. Okay, so these are the things what we have to remember. Now, when we take a look as how are we going to prepare? So, preparation of sulfates. So, when we take the metal of alkaline earth metal series in its simple form, or metal oxides, or metal hydroxides, or metal carbonates, and when we take these and react with sulfuric acid, we end up having the metal sulfates. Let's observe the reaction one by one. So, for the first one, let's say we have a simple metal. Okay, now this particular metal is going to be reacted with sulfuric acid, H2SO4. So, upon reaction with sulfuric acid, the sulfate section, the sulfate has SO4 minus 2 ions. Okay, so what is going to happen here is the sulfate is going to get connected with the metal, giving us metal sulfate MSO4, because metal over here is in a condition of M plus 2. Okay, now along with this there is a liberation of hydrogen. This happens when we take simple metal in its pure state and we react this one with sulfuric acid. Now, when we have the next one, and that is, let's start with metal oxide. When we have metal oxide and react this one with sulfuric acid, small change, that is metal sulfate is formed. Along with this there is a liberation of water. Okay, now let's take over here metal hydroxide and react this one with sulfuric acid. So upon this, it gives us metal sulfate. Along with the metal sulfate, there is liberation of 2 molecules of water. Let's check here. 2 into 2 is 4. 4 hydrogens and 2 oxygens. 2 hydrogens plus 2 hydrogens, 4 hydrogens and 2 oxygens. It's balanced. Okay, one metal, one sulfate section, one sulfate section. Okay, so let's observe the next reaction, and that is going to be with metal carbonates. So you can replace over here metal for this entire series. You can replace for the M as magnesium. Okay, we can replace it for magnesium, calcium, strontium, barium. Alright, so when we have this reacting with H2SO4, it will give us MSO4 plus carbonate section breaks down in order to give us carbon dioxide. Along with this, there is liberation of H2. So what we have here is the particular metal carbonate reacts with sulfuric acid in order to give metal sulfate. Along with this, 2 byproducts, carbon dioxide and water. Right? So this is how we prepare the sulfates. Right? We'll go further with the next reaction. Let's observe the next oxoacid, and that is going to be the nitrates. Okay, so how do we first form these nitrates? Quite simple as that. It is by treating the solutions of alkaline carbonates with dilute. Now, whenever we are writing DIL and with a dot over here, that represents a dilute. Okay, so dilute HNO3. Please don't call it as a dial HNO3. Dial HCl. No, it is a dilute HNO3. Alright, so when we react this one with the dilute nitric acid, what we get is the metal nitrates, and these metal nitrates are represented as NO3 twice, because the nitrate NO3 has -1 charge and your metals have a charge of +2. Okay, so therefore the combination will be like this. Now, here, whenever we have metal carbonates, because we are saying that we are taking metal carbonates, reacting these particular metal carbonates with dilute nitric acid. Okay, so therefore what is going to happen? Now, if I take over here MCO3 plus dilute nitric acid. Okay, so as these particular things will react, it is going to give me as NO3 twice. Alright, so along with this, there is liberation of carbon dioxide plus water. Okay, so 2 hydrogens, these are the 2 hydrogens. Out of CO3, we have only CO2 coming out. That means 1 oxygen is combining with these 2 hydrogens in order to form a water molecule. Okay, so these are your metal nitrates. Okay, so this is the metal nitrate. Alright, now, usually the metal nitrates of these alkaline earth metals are formed in unhydrated conditions. That means if we are taking over here MgNO3 twice, this particular compound is available in the hydrated condition as .6H2O. Okay, while if we see the elements at the end of the series, that is, if we take a look with respect to BaNO3 twice, that is a barium, the end element of the series. This is in an anhydrous condition. Okay, it is anhydrous. Anhydrous means there is an absence of water molecule in this compound, whereas there are a lot of water molecule in the starting elements of this particular series. That means as we travel from the top to the bottom in that particular set, the tendency to get hydrated goes on decreasing. So this is what we have to understand here, is that the tendency to get hydrated decreases down a group. So as we travel down a group, its tendency to get hydrated goes on decreasing. Okay, now why do they get hydrated? The starting elements, why do they get hydrated is because of, again, the smaller size. Smaller the size of an ion, more is the hydration enthalpy. Greater the hydration enthalpy, more hydrated the compounds are going to be. Okay, larger the size, less hydration enthalpy. Lesser the hydration enthalpy, anhydrous is the condition what is going to be formed. Okay, so this is how you have to remember. Okay, so here we end up with respect to the nitrates, and that is nothing more than the oxoacids. Okay, so this marks the end of the oxoacids of this particular condition. Let's observe the next one, and that is going to be yes, it is going to be the anomalous properties of beryllium. Why does beryllium show anomalous properties? Okay, so when we observe beryllium, first thing that we have to know is this beryllium has very smaller size. Okay, due to the smaller size of atom, that is in its atomic state and in its ionic state. This is the prime condition, this is a prime reason why beryllium is going to show us anomalous in its properties. Okay, so because of its smaller size of atom as well as in its ionic form, this thing has a higher ionization enthalpy. Due to higher ionization enthalpy, now everything is related, correct? So due to the higher ionization enthalpy, this particular thing forms a compound, or it forms the compounds which are actually covalent in nature. Okay, this is where everything starts to differ. Because of the covalent bond, the beryllium compounds show the properties which are not similar to the other elements of the same series. Okay, so therefore, these are the reasons why we are going to get anomalous properties of beryllium. Now, it's time to see as what are the different anomalous properties. So, properties. What are the properties? Property that what we have here is that beryllium is the hardest element in that particular series. The first thing is beryllium is the hardest element in the series. Second thing that we have to understand is beryllium forms the oxides. These oxides are amphoteric in nature, right? While the other element oxides are basic in their characters. Okay, so third point is about the coordination. The number of groups, the number of atoms it can have beside itself. If we observe about the beryllium, the number of bonds it can form. Okay, this beryllium can have a coordination number of 4 because of the involvement of 4 orbitals, because it has just 4 orbitals. While the other elements, if we observe the other elements, these other elements have a capacity of the coordination number as 6, because here there is an involvement of the different, even the d orbitals are involved in this particular case of the other elements. But in the case of beryllium, there is only s orbital and there are the p orbitals. So 3 p orbitals and 1 s orbitals are going to give us 4 orbitals. Okay, so those 4 orbitals give rise to 4 coordination numbers. Okay, So in the other elements, there is an involvement of the d orbital also, which gave rise to the formation of the coordination number 6 for the other elements. So these are the anomalous property of beryllium. Okay, so let's observe the last section for today, and that is going to be the diagonal relationships. Okay, there is a diagonal relationship between beryllium and aluminium. Okay, so when we take a look into the compounds of beryllium and aluminium, there are certain similarities which we are going to discuss now. The first similarity that what we can see is just like aluminium. Okay, even beryllium forms compounds that is an oxides. Okay, so just like beryllium and aluminium over here, okay, when we compare these two, what we see is beryllium forms the compounds which are not readily oxidized by air. It is because these particular things are going to form a layer of oxides, which will prevent its further oxidation. Okay, so therefore these are not readily attacked by oxygen because it forms a thin layer of oxide on the top. Okay, second thing that what we see is about the beryllium and aluminium is that in both the cases of halides, let's say about the beryllium chloride and aluminium chloride, in both of these particular cases, these things have the bridged carbon as what we had seen previously about the chain type of structures. Okay, in the same thing happens in both of the cases. In both of the cases we have the bridged chloride ion. Okay, and these particular compounds are strong Lewis acids. These are also used as catalysts in Friedel-Crafts reactions. Okay, so these are the things what we have to remember. Beryllium chloride and aluminium chloride, they have bridged carbons. That is a carbon between the two atoms of aluminium or two atoms of beryllium. Okay, those are called as a bridged chloride ions. These compounds, both of these compounds are acting as a stronger Lewis acids. Both of these can be used as a catalyst in the Friedel-Crafts reactions. Okay, so moving further, here we have this beryllium, okay, and aluminium. These particular elements dissolve in excess of base, or I can call it as an alkali solution. Okay, it dissolves in excess of alkali solutions in order to form, if it is beryllium, it will form pellerite ion. If it is aluminium, it will form aluminate ion. Okay, so pellerite ion BeOH 4 times minus 2, aluminate ion AlOH 4 times minus 1. Okay, so these are the things over there. In both the cases, that is for the Be and aluminium, both of these have tendency to form complexes. Okay, so these are going to form complexes. Complexes such as BeF4 minus 2 AlF6 minus 2. Here we end with respect to the diagonal relationship of beryllium and aluminium. So, take care, have a great day.